Welcome all. So today we will deep dive into the effect of blast loading. So in today's lecture we will be dealing with the blast effects and the design requirements associated with that. So let us start the lecture. So what is blast loading? Blast loading, as we have seen earlier in the previous lectures, it is a rapid high intensity pressure wave formation from explosion which impacts the structure. Okay. So if we look closely into the blast loading, okay, and if we categorize it as a pressure loading, then we will see that it follows this kind of signature. Okay. So this is pressure and this is time t. Okay. So it has a very steep rise. Okay. So this steep rise time normally is in nanoseconds. It is in nanoseconds. Okay. After it attaining a peak pressure, it tries to die down. Okay. And this regime is in milliseconds. Okay. So this is the positive phase duration, and after that the negative phase duration occurs. Okay. So both these two events are in the range of milliseconds. Okay. And the strength of the pressure depending upon the explosion can be in terms of kilopascals. Okay. And this signature, okay, it is known as a Friedlander's profile. Okay. So this signature can be from the overpressure also, and it can be from the reflected pressure also. We will discuss what does we mean by that. Okay. So main concern from the blast pressure comes from the overpressure. Okay. That is the pressure front that is formed and it hits the structure. In addition to the pressure, okay, there will be fragments. Okay. If this blast material, okay, let us say TNT, if it is kept inside a steel casing, okay, a very hardened steel casing. So once the blast occurs, these casings will be fragmented, okay, and they will fly towards the structure. Okay. So this fragmentation process is also a concern, okay, because it can damage the structure and it is with a very high velocity. Okay. And there is a shock front also that forms during a blast load. Okay. So these three things are the main concern during a blast loading. Okay. So our purpose as a designer is to safeguard the personnel, okay, the person sitting inside a building, a vehicle, or any other establishment. After that, we also have to protect the equipments. Okay. Let us say if the building is serving as a data center or it is storing high ammunitions, so we have to protect the equipments that are associated with it, and also we need to prevent the propagation of the explosions. Okay. So once the blast pressure hits a structure, okay, there will be reflections, and due to the reflections the intensity of the pressure will increase. Okay. So this will help in propagation of the explosion. Okay. Or if one explosion occurs here, okay, and its intensity might hit the other explosive material kept nearby. Okay. And these things can also be ignited. Okay. So this thing normally happens during an ammunition container. Okay. So this is called a sympathetic blast. So we have to prevent the propagation of explosion also. Okay. So here we can see a diagram in which the propagation of blast loading is shown. Okay. So here the example of a truck filled with explosive is taken and the explosion occurs near a building. Okay. So once the explosion occurs, the blast pressures will travel and hit the building. Okay. So this blast pressure, okay, which hits the building, okay, they are called the reflected pressures, because here the pressure is being caused by the blast explosion and it is being interacted with the structure. So this becomes the reflected pressure. Where there is no interaction, okay, like in the sideways, it is called an overpressure. Okay. So moving ahead. So detonation. So we are defining some terms associated with the blast loading. So first term defined is detonation. So what is detonation? Detonation is a very rapid and stable chemical reaction traveling through the explosive material at a supersonic speed, and this supersonic speed is called the detonation velocity. So if we have a blast charge, okay, let us say we have a TNT, okay, so there will be a detonator and initially the detonator will be ignited, okay, and this detonator will cause the a chemical reaction to propagate through the base material, okay, and this propagation will through a supersonic speed, okay, and this supersonic speed is called a detonation velocity, okay. So, typical detonation velocities for most high explosive range from 22,000 to 28,000 feet per second, okay, or roughly 7,000 meter per second to around 8 to 9,000 meter per second, okay. So, this is the typical range of the detonation velocities, okay. It means that the chemical effect caused by the detonator will cause the waves to propagate with a very high velocity of 7,000 to 8 to 9,000 meter per second or 22,000 to 28,000 feet per second, okay. So, what does the detonation wave does? So, the detonation wave converts the explosive solid or liquid into hot dense high pressure gas, which initiates strong blast waves in the surrounding air, okay. So, this is the, it is basically a igniter, you can call it as a igniter also, okay. So, this is the simplest example explanation of a detonation. So, detonation pressure and energy release, okay. So, pressure immediately behind the detonation front are extremely high, okay, ranging from 2 million to 2.7 million to around or roughly 3 million to 5 million psi, okay. So, if the detonation has occurred, okay, and if here we are measuring the pressure, here the pressure will be around 3 million to 5 million psi, okay. Only about 1/3 of the total chemical energy is released during detonation, okay. The remaining 2/3 of the energy are released more slowly after burning, okay, when detonation products mix with air and burn, okay. After burning has a, so the 2/3 remaining, okay, which after burns has a minimal effect on blast wave properties due to its much slower reaction rate relative to the detonation, okay. Blast wave formation, okay. So, how the blast wave is forming? The explosion produces a shock wave characterized by a high intensity shock front that expands spherically outwards from the explosive surface, okay. So, if the explosives have occurred, there will be a formation of the shock front, okay, and let us assume that this thing is kept in air, okay. So, this is how the shock front will be propagating spherically outwards, okay. As the blast wave propagates, there will be a decay in the strength, okay. So, here if we try to measure, okay, so there will be a gradual decay in the strength, okay. So, duration will also lengthen and the propagation velocity will decrease, okay. So, this decay is caused by spherical divergence and the completion of the chemical reaction, okay, except after burning, whatever is the chemical reaction, that is completing very fast, okay. So, the blast wave will deteriorate, okay. Now comes the interaction of the blast wave with structures. So, the shock front first impedes the structures in its path, okay. It means that this shock front, this travelling shock front will hit the structure in its path, okay. Slowly the entire structure is enveloped by the shock pressure, okay. So, after that the shock pressure will be around the entire structure, okay. The magnitude and distribution of blast load on the structure depends upon two properties, okay. One is the explosive properties like the type of charge, energy output, okay, and weight of the charge, okay. Then it also depends upon the detonation location relative to the protective structure, okay, where the blast has occurred, okay. What is the strength of the blast, that is how much charge is there and at what distance it has occurred from the structure, okay. After that there is an interaction between the blast wave and the structure. So, due to this there will be a pressure reinforcement due to reflection and interaction with the ground or structural element, okay. As this thing, okay, tries to reflect with the ground or it tries to reflect from the structure, okay, there will be an increase in the strength of the blast load, okay. So, blast load has two components, one will be from the signature of the blast, okay. So, the weight of the blast and the distance from the structure where it is kept, and after the detonation has occurred, okay, once this pressure hits through the ground or it is interacting with the structure, okay. So, due to these two interactions there will be an increase in the strength of the blast load. Okay. So, the pressure that is moving from the blast only, that is called the overpressure, and the pressure which is interacting with the structure, that is called a reflected pressure, and the reflected pressure might be significantly higher than the overpressure. Okay. So, here is the similar graph that we were discussing earlier. Okay. So, if you look very closely, this thing is actually rises like this. Okay. And this phase is very small. Okay. So, it is in nanoseconds. Okay. So, the shock front is marked by a nearby instant jump from ambient pressure to peak incident pressure. Okay. So, if this is the ambient pressure, okay, so there is a sudden jump from the ambient pressure. Okay. If this is the ambient pressure, a blast occurs, okay, and there is a steep jump from the ambient pressure to the peak incident pressure. Okay. So, here there is a jump. Okay. So, behind the shock front, the molecules move at lower velocities, okay, or the particle velocity, generating dynamic wind pressure. Okay. Following with the pressure dropping below ambient. So, after the ambient pressure has occurred, okay, the pressure will try to die down and there will be a pressure decrease here, okay, due to the suction effects. Okay. So, this is called the positive phase duration and this is called the negative phase duration. Okay. Positive phase duration and negative phase duration. So, this is the magnitude of the positive pressure and this is the magnitude of the negative pressure. Okay. So, there is a negative pressure and the air flows reverses, basically the suction is occurring here. This lasts longer than the positive phase, but with the less intensity. So, here we can see that the duration of the negative phase is larger than the positive phase. Generally it is larger than the positive phase, but the intensity of the negative phase is less than the positive phase. So, PESO positive is greater than the negative phase duration. Okay. And this profile is called the Friedlander's profile. Okay. So, this is called Friedlander's profile. Okay. So, pressure decay and duration. Expansion effect. As the blast expands into a larger volume, peak pressure falls and the pressure duration increases due to the energy spreading. Okay. So, this can be is shown in the figure. Okay. So, figure 3 discusses the pressure duration and the other properties depending upon the distance and intensities. Okay. So, here we are denoting the peak incident pressure. Okay. It means that we are denoting the this thing, peak incident pressure. Okay. And peak incident pressure versus peak dynamic pressure. Okay. So, this is the peak incident pressure with respect to the peak dynamic pressure, density of peak dynamic pressure, particle velocity and density of air behind the shock front. Okay. So, as we can see, okay, with the increase we can see that the behavior of the peak dynamic pressure, okay, behavior of the particle velocity, okay, and this is the behavior of the particle velocity and behavior of the density of air behind the shock front. Okay. So, blast wavelength. Okay. So, positive wavelength, the distance zone experiencing positive pressure at a given instant. Okay. Negative wavelength, the corresponding distance for the negative pressure. Okay. So, these are the definitions of the two blast wavelength. Okay. So, explosive materials. Okay. So, explosive can be made from different materials. Okay. It can be made from solids, it can be made from liquids and it can be made from gases. Okay. Like TNT is the most commonly available explosives. Okay. So, as we have seen earlier, okay, high explosives will detonate with a supersonic reaction front, okay, and detonation velocities are around 22,000 to 28,000 feet per second. And only some part of some materials detonate, okay, remainder may burn slower. Okay. That is, we have seen, this is called the after burn. Okay. So, the shape of the explosives affect blast parameters and this is shown in the figure. Okay. So, the explosives can be made of orthorhombic material, okay. It can be hemispherical, it can be in process of a hopper, okay, like this. It can be grenades, okay, small billets can be there. Okay. It can be in the form of close-up hopper, pressed billets, extruded rods, projectiles, beakers, cylindrical, spherical, carpets, bags. Okay. So, depending upon the shape of the explosives, the blast parameters are affected. Okay. So, different shape will give the different intensity of pressure, even if they are made up of same material. Okay. So, one parameter is material, other parameter is shape. Okay. So, in order to get a standard effect, okay, one term is being introduced, okay, and that is called the TNT equivalency. Okay. So, what TNT equivalency does is it standardizes the blast effects, and the comparison between different explosives can be made. Okay. Simply means that, let us say there are 4 or 5 or n number of different explosives, explosive 1, 2, 3, 4, 5, 6. Okay. They are of different mass, okay, and different shapes. Okay. Now, we have to, and any different type of explosives can be made using different compositions. Okay. So, now if you want to express or if you want to analyze the effect of so many number of explosives, okay, there it will be very difficult to us. Okay. So, in order to have an equivalency, okay, everything is expressed in terms of TNT. Okay. So, equivalent amount of TNT is the base unit in blast loading. Okay. In blast teaching, okay, everything is expressed in terms of TNT equivalency. Okay. So, here we are expressing the WE as TNT equivalent charge weight. Okay. This is different from the actual TNT. Okay. Here a TNT equivalent has been used. Okay. So, a TNT equivalent charge weight is being used. Okay. And we can take any explosives, okay, and we can express the effect of this any explosives in terms of the equivalent amount of TNT. Okay. So, what we can do is that if you want to compare effects of different types of explosives, what we can do is that we can convert them into equivalent TNT. Okay. So, this value might be 1 equivalent TNT, equivalent TNT 2. Okay. And now, since they are all equivalent in the same units, we can compare them and we can see which one is producing the maximum pressure or maximum positive duration or any other parameter. Okay. And H is used to denote the heat of detonation of explosive of the any unknown explosives or known explosives and TNT respectively. Okay. And since this is a very uncertain area, a 20% safety factor is applied to account for the uncertainties. Okay. So, basically the effect of any type of explosives is expressed in terms of equivalent amount of TNT. Okay. So, the TNT equivalent amount of TNT or equivalent amount of kg of TNT becomes our base units in whenever we are talking about the blast loading. Okay. Actually, any type of explosives can be used, okay, handmade or any other produced depending upon the requirement, but when we are doing the analysis, we will always convert them into an equivalent amount of TNT, okay, depending upon their heat of detonation. Okay. So, TNT equivalency or equivalent amount of TNT becomes our base unit. Okay. So, in blast loading, this is the base unit. Okay. Okay. So, the categories of blast loading. Okay. So, blast loading or explosion can be categorized into two parts, confined and unconfined. Okay. The blast can occur in air or it can occur in ground or anywhere, and it might be contained in a box or a building or any type of container, or it can be free. Okay. So, if it is unconfined, there is the free air burst and the surface burst, okay, depending upon the location of the blast with respect to the ground. Okay. Confined, if it is confined, then it is termed in terms of the ventilation. Okay. Fully vented means significant number of air vents are there. so that the pressure may go out. Partially confined, the amount of ventilation is restricted, and fully confined, no ventilation is there. Okay. So, the confined blast and unconfined blast, okay, has a different signature. Okay. So, let us say we have taken same amount of TNT, let us say we have taken 1 kg of TNT for both unconfined and confined blast, okay, 1 kg of TNT. Okay. So, if we are taking free air burst, okay, or air burst, okay, what will happen is that the reflected waves, okay, the reflections will be minimal. Okay. So, only reflections caused will be either from the ground or from the structure. Okay. Rest it is free to dissipate in the air, but this if it is occurring in the fully confined way, okay, there will be a lot of reflections, okay, because the pressure has nowhere to go. Okay. So, what will happen is that the intensity of the reflected pressure will be increasing. Okay. So, if we measure in this confinement and if we measure here, okay, the intensity of the reflected pressure will be more in confined air. Okay. So, if we are doing a confined blast, even for a very less amount of blast, we can see a very large pressure formation. Okay. So, the confined blast is more deadly than a unconfined blast. Okay. So, let us say we have an explosion in a reinforced concrete building, okay, where there is zero ventilation, okay, it is fully confined, okay, and if the same explosions occurs, okay, in very shed type of structure, okay, and same amount of explosive is being used. So, okay, so the effect of the reflections from the structure will be minimal in case of the unconfined blast, but in case of a fully reinforced concrete structure with full confinement, the effect of the pressure will be more. Okay. And these examples are well documented in the history also, where the fully confined blast was assumed, but later on this happened in an unconfined region and the effect was minimal. Okay. So, we can see this across the history also, okay, and we will try to see some calculations related to this also. Okay. Okay. So, now we will talk about the different types of explosions. Okay. One by one we will be talking about each of them. So, first we will talk about the free air burst explosion. Okay. So, definition of a free air burst explosion. In a free air burst explosion, it occurs when the detonation happens adjacent to and above a protective structure. Okay. So, the detonation is happening here. Okay. It is above, okay, and it is nearby a protective structure. Okay. So, this explosion is nearby the protective structure and it is happening above the protective structures, okay, with no amplification of the shock wave between the explosive source and the protective source. Okay. So, there is no amplification between the explosive source and the protective structures. Okay. So, this is a free air burst environment. Okay. So, the blast wave propagation, the shock wave radiates spherically. Okay. It is radiating spherically from the detonation center. From here it is radiating spherically and it is moving outward through the air and strike the structure directly without intermediate reflections or reinforcing. It means that there is no reflections associated with this type of explosion. Okay. So, if the explosions occur nearby a structure and it is above it and there are no reflections, okay, to the blast wave propagation, then it is categorized as a free air burst explosion. Okay. And this is the ground surface. So, even from the ground surface or after hitting the structure, there is no effect of the reflections, okay, and it is spherically propagating. Okay. So, this is called a free air burst explosion. Okay. So, in a free air burst explosion, when the blast wave impacts the structure, the initial wave pressure and impulse are reinforced and reflected at the surface. Okay. The reflected pressure pulse can be significantly greater than the incident pressure at the point of normal incidence. Okay. This reflected blast load profile on the structure follows typical infinite plane reflective behavior. Okay. Okay. So, pressure variation on surface. Okay. Peak pressure and the impulse vary with distance from the normal point of impact. Okay. The maximum normal reflected pressure occurs at the point where the blast wave arrives perpendicular to the surface. Okay. So, here we can see the blast wave propagation has no reflections on the no reflections. Okay. The wave pressure, okay, they are reinforced and are reflected at the surface. Okay. Okay. So, in an airburst free airburst environment we can see the blast wave, okay, it is propagating and there is no reflection in the blast waves. Okay. The shock waves or the blast waves have no amplification. Okay. But the pressure waves, okay, pressure waves and impulses are reflected at the surface. Okay. And these reflected pressures can be significantly greater than the incident pressure at the point of normal incidence. Okay. So, if we remove the structure, if we remove the entire structure from here, okay, and if we measure the blast pressure, okay, at any point, okay, so the incident pressure will look something like this. Okay. But if this structure is there, okay, during a free air burst, okay, then due to the reflections the reflected wave can be significantly higher. Okay. So, this is the overpressure and this is the reflected pressure. Okay. So, the wave pressure and the blast wave pressure and impulses are reinforced and reflected at the surface. Okay. The reflected pressure can be significantly greater than the incident pressure at the point of normal incidence. Okay. This reflected blast load profile on the structure follows typical infinite plane reflective behavior. Okay. Pressure variation on surface. Okay. The peak pressure and impulse vary with distance from the normal point of impact. Okay. It means that the amount of pressure measured here and the amount of pressure measured here and the amount of pressure measured here will be a function of the charge of the explosives, the distance of the explosives and the reflections. Okay. So, the incident pressure will be a function of the charge of the explosives and this distance. Okay. So, this will be R1, this will be R2 and this will be R3. So, since the charge is same for all these 3 points and the distance is varying, so the incident pressure will be varying at all the 3 points. Okay. Maximum or the normal reflected pressure occurs at the point where the blast waves arrives perpendicular to the surface. Okay. So, the maximum intensity of the reflected wave will be at this point. Okay. Why at this point? Because here the travel distance is minimum. Okay. So, since the travel distance is minimum, the maximum intensity of the reflected pressure will be recorded here only. Okay. The peak pressure and the impulse reduce to the incident values as the angle between the wave propagation and the surface normal increases. Okay. As this distance increases, okay, the intensity of the reflected pressure also dies down. Okay. And there will be a point where the incident pressure and the reflected pressure will be same. Okay. So, this is the free airburst explosion. Okay. Scale distance and the blast parameter curves. Okay. Earlier we have seen the TNT equivalency. Okay. So, the TNT equivalency was used to establish the effect of the different weights and different types of chemical used for the explosion. Okay. The scale distance parameter and blast parameter curve is used to establish the effect of the pressure depending upon the amount of the charge and the distance from the charge. Okay. Let us say we have a building out here, okay, and charge occurs. Okay. So, the amount of incident pressure, okay, will be a function of the weight and the distance. Okay. So, if we are measuring pressure here, okay, so there can be different combination of W1 and R1, okay, which will give me the same value of P. Okay. So, in order to have this equivalency, okay, a term is used that is called the scale distance, a parameter z, which is a function of r, that is the perpendicular distance, and weight, okay, that is the amount of charge, okay, where r is called the standoff distance, okay, that is the perpendicular distance between the charge and the point at which it is measured, and w is the charge weight. Okay. Since we are considering spherical charges, we normally consider spherical charges. So, this cubic root is used, okay, in order to change from the volume to the normal charge. Okay. So, this term is used to generalize the blast effect. Okay. It simply means that different weights and different standoff distances will produce the same effect of the blast pressure. Okay. So, this term is used to find that equivalency. Okay. In the similar way, equivalent amount of TNT was used to find the generic pattern or generic effect of the blast pressure. Okay. So, now we have learnt about the different blast parameters, okay, peak pressure, impulses and durations. Okay. Impulses is nothing but the area under the pressure time curve. Okay. So, that this area will be positive impulse and this area will be the negative impulse. Okay. So, this is the area under the pressure time curve, okay, and their variation is based on the z. Okay. So, z is a parameter, the scale distance that is used for the protective design. Okay. Here charge weight, we have already established a equivalence quantity, that is the TNT equivalency. Okay. So, whatever type of charges are made, we will always express them in terms of the equivalent amount of TNT. Okay. So, using this parameters, okay, we can produce design charts, okay, where we can see the effect of the blast pressure, we can see the effect of the impulses, we can see the effect of the duration based on the standoff distances and the equivalent charge weight. Okay. So, this type of design charts, okay, are normally they are upper limit and they are very conservative. Okay. Since we are using them for engineering design and calculations, okay, we always tend to have a conservative upper limit effect, so that our structures are safe. Okay. So, this type of design charts can be developed. Okay. So, depending upon W and R, different type of pressure curves, reflected pressure curve, over pressure curve, okay, impulse curve, okay, and time duration curve can be developed. Okay. Where if we just know the weight of the charge and the standoff distance, we can calculate all these parameters. Okay. Similarly, we can develop charts, okay, such that if we know the signature of the structure, okay, we can calculate the displacement, okay, depending upon the different z values. Okay. So, if we have the signature of the structure, we have the signature of the blast associated with that, we can calculate the displacements, we can calculate the stresses, and we can calculate the other parameters affect with that. Okay. So, this type of developments we will continue in this lecture. Thank you for today.